Conversation on the way here, so I'm a little late. Turns out I lost my last grant attempt, which is really lethal to me because a reviewer claimed I falsified it, which is great. Gotta love it when that happens. So basically, it said I intentionally undercharacterized the materials we were working with so that I could lie about the results, which you know is a really bold thing to do. But the problem with scientific research right now is that all reviews are done anonymously, and there's no consequence. In other words, you can lie. You can lie and get away with it. That's what everyone chooses to do now. Lie. Lie to punish people you don't like and to reward your friends. So if a friend gets your proposal, you will get it. If you have to get randomly lucky and have your friend review your proposal, that's just random. When it happens, you win. When it doesn't happen, you lose. If a person, there's been studies on this, when a person has a grant or paper reviewed by someone they don't know, they will lose every time. So anyway, I'm the one happy, all right? Not even Abner the invisible dog can cheer me up. So, how could you not be cheered up by Abner? Abner, critically depressed. Now, you gotta admit that was hilarious. Like sometimes I see a movie and I'm like, that was bad acting. But then I look at Abner the invisible dog, I'm like, no, that's bad acting. Anyway, I like to make fun of children too. Okay, so. All right, review of last time. There's not much to say. I'm not even going to write an example. Electrochem. I did have. I'm sorry I was late. I did just post the video from Friday. The electrochem is so easy. Again, remember, I do want you to. Excuse me. I do want you to show me that you know that you need to translate EMFs to delta Gs. You add the delta Gs and go back to EMFs. So I'll have one question. That's very, very, very easy. All right. And remember, that's just this translating to delta G. So you can add energies, that's Hess's law, but then you got to translate it back. So just show me you can do that, but then you know the real trick is figure out the dominant reaction, get the other one to conform, and then do stoichiometry so that you can write out the full reaction. That'll be a third of the point. But you know, without scaling, once you get the directions right, you just add the EMF. So remember, if you have to flip one, don't scale it. But if you flip it, make it negative. Right? That's all you got to do. And that way, the point of that is double checking. If you just write down an answer, you know I can't give you really any credit for that because I don't know if you worked it out in your head, which is possible. I think that's why I was so floundering last time. I don't know what was wrong with me. I haven't reviewed my notes, but if you hadn't seen the video, if you weren't here and you hadn't seen the video, it's me floundering like a fish. At the end of the day, with your help, I did get the questions right, so you should be fine on your homework. The homework's very, very, very easy. So I don't want to say too much more about electrochem. Again, I'll have one or two true and false. I'll have straight up potentials. Please give me the EMF. Please give me the reaction. That's pretty obvious. It's 3 points. Okay, and so with that, that's really a Hess's law deal. That's really it. I mean, we're kind of done. Once I've finished all these reaction Gs, for reactions we want to know the equilibrium because it tells us how far the reaction goes. For electrochem, we don't really want equilibrium. We want the battery to be charged, and that's actually not equilibrium. You see how easy that is. And that's it. So the rest of our there really is no more thermo. We're really done with thermo now. And so the rest of it's really just a lot of stuff. And so I warned you, I don't like this part of the class, but again, if it's on the GRE, if it's on an MCAT, I have to go over it. Otherwise, I'm screwing you badly. And I'm not going to do that. So, phase, here, let me title this, phase diagrams. So we got about a week on phase diagrams. Again, I hope you brought your chin stick. Like it's okay if you fall asleep, because I might fall asleep. It'd be funny if we all just fell asleep and then just woke up and pretended that nothing ever happened, right? So, anyway, so actually, let me just stop before I get into this stuff. Any questions? We're okay. No class business. There's not much to say, right? You got your homework. It's very easy. Is that, what are you on, almost at 9 or 8? 9, okay, so I might just have one more problem set. Because if I have a third one, that means that you'll have a test, a final, and a problem set all due within a week and your other exams. I'm not inclined to do that to you, all right? But if there's material that you need to see, so I mean, I can't do it. I mean, it's too much for me to grade. I have to help grade as well. I got short with. So I probably we're going to have our next to last problem set. Probably this is the next to last problem set, sorry. Other class businesses, actually the calendar screwed up. Next week, I accidentally repeated, Henry's Law is supposedly next week, and we've already done it, so if you're reading the calendar, it's screwed up. Just ignore next week and go to the next week. And we're pretty much on the calendar, except for the calendar's screwed up. So anyway, if you're reading along, don't look at next week. I'll try to fix it. I'll fix it at some point, but I gotta send something out. Anyway, blah, blah, blah. Okay, phase diagrams. No questions, or phase diagrams. Okay, so this is a one component phase diagram. So that means that this is water, essentially. Actually, I've drawn this very similar to water. And it's, again, childishly simple. Solids, liquids, gases, and critical. So I'll get into a bit more detail on the critical phase. But the important thing to know is, what am I bloody likely going to have on a test? I'm going to have this unlabeled, something like that. I'm not saying I'm going to do that. I've done it before, so I'm likely going to do it, but I might. I throw this at you, and there's nothing labeled. I said, label everything. Okay, what do you do? Now, low temperature, high pressure solids, right? High temperature, low pressure gas, that's easy. Liquid's the only thing that remains. I'm surprised that sometimes people still get this wrong. It's very easy. And other things to note is that this is a triple point. Where all three phases are simultaneous. Notice that it occurs at a very specific temperature and pressure. It's actually really, really hard to hit something in the triple point because you have to have extremely good control of pressure and temperature. There's actually a good, one of those new science shows on like Nat Geo, I watch that all the time, had a really neat example of a triple point. And I'll see if I can find it and I'll post it. And critical's kind of cool. That's its own phase. It's not a plasma, all right? So plasma is like out here. We're not doing plasmas, all right? That's technically a phase, but I'm not going to go into it because, you know, I guess you run into plasmas during welding. That's how arc welders work. A stream of like argon is a good gas, and then you have a charge that goes on between it. And what happens is as soon as one argon atom is ionized, it then is very good at ionizing the other argon, so it just kind of kicks in. And anyway, so yeah, everyone always, I don't know why, everyone always asks me about where are plasmas. It's good enough. All right, so critical phase is neither liquid nor gas. It has, critical liquids, critical fluids, you hear about critical gases, critical liquids. They're really kind of interesting in that the properties, you can imagine if you're here, you are liquid-like, if you're here, you're gas-like, but you're still different. And just to emphasize exactly how are you different, we don't have it. Things like, all right, so xenon and CO2 in this region, if you can get them critical, they're actually as good a solvent as water. And so people at one point, actually, when I was in North Carolina, I worked for two different professors. They collaborated very closely, so it's kind of natural that I kind of went in between them. And one of them, as I was leaving for California to grad school, I looked in this publication. You know how publications, mainstream publications, like to have little science junkets in there that are usually dead wrong. Well, it was about him. And he had actually built a dry cleaning device based on supercritical CO2. It's really clever, went out of business. Why? Because it's insanely dangerous. That's the only slight problem. And so what happens is critical regions, to get a liquid or gas to turn critical, these temperatures and these pressures, they're big numbers. So this is mucho dangerous, right? So anytime, now, I think I told you this before, if you're working in various research labs or I don't know, whatever setting, 2 atmospheres of pressure, that's actually kind of dangerous. Cheap glass will shatter at about 2 atmospheres. I mean, your brain can almost make 2 atmospheres. So if you're ever dealing with anything that's under pressure, be really freaking careful because it doesn't take a lot of pressure before something can, before you can get a really bad accident. What else do I want to say? Okay, one thing that's kind of important about the triple point. Here, let me write it. The triple point. So this is something that, in terms of, I've done this class so many times. What kinds of things will cause you to mess up questions on this? Triple point, there's more than one. Okay, now, for practical purposes, when it comes to solid liquids and gases, the triple point between them, there's usually only one of that type that has 3 phases of equilibrium. There are always 3 phases of equilibrium. One thing about it is that you can have more than one triple point, but they're going to be up here. What happens is solids have there's different types of solids, essentially. And I think they're called, any engineers do you know, I think for metals they're allotropes. Does that sound right? Right, different structure. You have hexagonal closed packed versus table salt, cubic. So those are very common. Hexagonal closed packed is common. But anyway, so when you're up here, you can pressurize whatever. You put water, you can pressurize water, get to new solids, and there should be triple points between them. Anyway, so I don't know how to draw that. It'd be something like this. I'm just kind of making this up, but anyway, and so this will be, so the point is that this has a certain structure, that has a different structure, that has a different structure. But from your perspective, it all looks the same, but from an X-ray perspective, I like to do X-ray work. From an X-ray perspective, they are completely different from each other. So again, don't screw this up. This is the number one question that people miss. In terms of, okay, so there's different solid phases, which is very sensible to understand. You know that there's different, we say rock, salt, things can transform between them. Liquids, there is helium, actually. Helium has 2 liquid phases. Now, I don't quite remember, it's something like this. It's like a line there, here's liquid 1, here's liquid 2. It's something like that. I don't quite remember off the top of my head. But the helium, the other liquid phase, is actually, I believe it's a Bose-Einstein condensate, which just means that as you, one of the things you're going to do in quantum is that a lot of things can only exist in one quantum state. So we're all like molecules, or better yet, we're all like electrons. I am going to be somewhere and nowhere else is allowed to be there. And the same for you. Now, when it comes to molecules, we can all sit in the same chair, essentially, whereas we can't if we're electrons. And so a Bose-Einstein condensate, which hopefully you'll see a little bit of it because they're really interesting, exists for helium. So helium has 2 liquid phases. That's the only material we've ever discovered that has 2 liquid phases. And as you can imagine, there's no such thing as 2 gas phases for helium or anything, right? They don't exist. There's only 1 gas phase, and that, it just doesn't make sense. It's really weird that there's actually 2 liquid phases of helium. The thing that's really neat about that is, because this material is so dry, I'm going to fall asleep. Let me tell you some of the interesting things about these Bose-Einstein condensates, like this other liquid helium. And people have actually done this. If you take a pool of it, of course you have to go really low temperature and high pressure and all that. I'm not going to set up a demo right here and do it. But if you have the contraption that can make this, imagine a pool of liquid helium, and you have a boat, and you just kick the boat. The boat goes on forever. There's no friction, so things can slide over it with absolutely no friction, and that's because they're all sitting in the same chair quantum mechanically. Again, that's the Bose-Einstein condensate. That's actually how you get superconductivity. Superconductivity is also a Bose-Einstein condensate, where the electrons move without friction, right? Just like the boat floats on the water with no friction, electrons move with no friction to electrons with resistance. Ergo no resistance, that's where we get superconductivity. And you need liquid helium to do that. So most things, you hear about high temperature superconductors, they don't work very well. For the most part, your MRIs, your NMRs, those have to use liquid helium because they just have, I think it's actually just like copper wire actually. If you get metals cold enough, they will turn superconductive. And guess what? You know how I like to talk about cancer, feline AIDS. So you need helium for your MRIs. You need an MRI if you ever have surgery. You're going to want an MRI, okay? The alternative are X-rays, and you don't want to get a good dose of those. It's not terrible, but if you can get an MRI, you're better off. And so for that, we need superconducting wires to make superconducting magnetic fields. That's how the whole imaging thing is done. And so we need helium. Guess what we're running out of? Helium. How did you, well, because I was talking about it, right, it makes sense. Guess where we get helium from? It's not the air, by the way, there's not enough helium in the air.
Wow.
Yeah, actually, you got right in the petroleum industry. Yeah, it's locked in oil, and it just comes, when you dig the oil out, when it's under pressure, the helium comes out. That's actually where our helium reserves are. So when we run out of oil, we run out of helium, no more MRIs. That's okay, because remember I told you Mad Max is actually a documentary from the future. Who's going to care when we're fighting each other? And so you really need to get like helmet pad, shoulder pads with spikes on them. Right, that's going to be necessary here in about 5 years. So the world is running out of helium, and it's okay because we're going to run out of oil at the same time. There's another neat thing, little facts. Since I'm full of factoids today, I might as well just run my mouth like an idiot. So there's a type of helium, isotope, helium-3, that you need to get to the super cold temperatures that, for different research purposes. We're running out. Here's why. All right, so the dangerous thing about helium is if you release it, it goes to the upper atmosphere and keeps going. Earth's gravity is not strong enough to hold helium down. So every helium balloon you've ever had, that helium, actually, the reason it deflates, it's like, oh, what a bad balloon. No balloon can hold helium. Helium is small enough that it can get in between molecules of the plastic that make the balloon. So that balloon's going to deflate. That helium goes up and it keeps going and it leaves the planet itself. That's why we're losing helium. This helium-3 that I told you about, which again was stupidly invented, we have it because it's a natural byproduct of plutonium production. So once we built the first atomic bomb, which was a uranium bomb, and then we figured out plutonium was much better at killing, so we ended up producing a lot of plutonium. That was actually done in Washington State, in the eastern half, which is a desert, at the Pacific Northwest National Lab. That was our main plutonium production facility. That's where we got all our helium-3. Well, we stopped making bombs, thank God. We stopped making bombs because it became pointless, but the world simultaneously slowly started running out of helium-3. We're almost out to zero now. This stuff was like $5 a bottle, now it's like $50,000 a bottle. That's how serious it got. So our need for helium-3 is so great. Get this, our DOE is considering restarting plutonium production just to get the helium-3, not the plutonium. No one wants the plutonium, but we want the helium-3, so we might actually do that. Okay, blah, blah, blah. Anyway, all right, random noise. I hope it makes this stuff a little bit more interesting. Okay, so I gotta start talking about this again. Let me tell you a little bit more about the critical, and I have a video of this. I'll post that shortly. Again, critical phase research, something I actually kind of got involved with at one point. Requires high temperature, high pressure. Generally, like if I wanted to research this stuff in my lab, I would actually need to get a license from the fire department. Also, if you have like certain very poisonous gases like fluorine, you also need a license from the fire department. They want to know who you are, and they want to know where this stuff is in case there's an accident. That's why you have to do that. Okay, but anyway, if you ever, I'll post a video. What you see, if you look inside the magic box, you can see a liquid. All right, so you see a liquid in there, and then what happens is the system goes critical. The boundary between liquid and gas gets nebulous. And you just see this layer of fuzz start at the inner, when you go from an obvious interface, it just gets fuzzy, and then it's just not there. Then it's like it just disappears, like it evaporated, but like really freaking quick. And then the cool thing is this video, this guy in England that actually he and I used to do similar research. What he does is he then cools the thing back down and it starts to rain. So anyway, that's kind of neat. Just to emphasize, one of my little pet things is that the critical region is terribly, terribly different than any other. Let's see, I guess that's all I want to say about that. All right, here's some, I'm going to have to draw this again, but I'm going to draw it more accurately. It's going to be more. Yeah, one of the times I should probably PowerPoint, but screw it, here I am. I'm already here, I might as well just do what I'm doing. So I'm gonna put down some real numbers for water. Water does a couple of things that are kind of unique. And okay, again, we get this little exponential-like curve. And this is around, okay, so Understand that means break. What the hell? These are torrs. Or no, Pascal. What's wrong with Pascal? So this is about 600. Okay, this is a break, you know what I mean? And so then this is 101,325. Okay, that's atmospheric. Okay, let's see, we go this way. We go this way. And let's put ourselves at, let's see, what am I doing? What am I doing something wrong here? No, I'm not doing something wrong. 373, temperature in Kelvin. Sorry, temperature in Kelvin. So let's put ourselves right here. And, sorry, that's, no, I did this wrong, sorry. So this has to be like that. Sorry, you see what I have to do at 373? I better be at 1 atmosphere, because then I should have a gas. So I'm not showing the critical. Okay, so you saw what I screwed up there? 373 at 1 atmosphere, I better be on the liquid gas line, right, 100 degrees C. So, what kind of things I do wrong when I draw things wrong. Okay, now, here's a really neat thing about a phase diagram. Let's drop this at 300. Okay, so room temperature. Okay, one of the neat things about these phase diagrams is that there's actually a lot more information in here than you might realize. All right, for one, again, if I move over here, I can see the boiling point pressure, and I can see that also if I decrease pressure by like climbing up Mount Everest, which is apparently full of 200 dead bodies, if I lower pressure, I'm going to lower my boiling point, which is why you have to go things longer if you go higher up. You already know that. Okay, now here's another neat thing, and I meant to bring a demo. Oh, I got a demo. Guess what I'm going to do?
You can evaporate water.
It's the same demo every time, isn't it? It's me and a cup of water. I don't have to bring a cup of water. Okay, so what's going to happen? It's going to evaporate, right? Hold on a second. We're on the liquid region. Never thought of that before, did you? We're in the liquid state. How in the hell do I have any gas at all? Right? You know this is going to evaporate. Eventually all of it evaporates. It sounds like I'm in the gas region. I'm not. I'm in the liquid region. How can that be? How can I be in the liquid region yet this turns into a gas? Isn't that kind of nuts? Well, I'll explain in a minute. You probably don't know this. There's a really cool reason why that is going to evaporate. You probably just think, oh, water evaporates. It does it for a very interesting reason. Now, again, hidden things on a phase diagram. Let's go to our present state. If I go this way, I know that I have to heat things up and eventually I get a gas at 100 degrees Celsius. I know that. But if I look down and then look over, which is around 600 pascals, guess what does that number mean anything?
Yes.
What do you think it means? Remember my little sniffer I told you about? Remember when we were doing reactions and mixing in Henry's Law? I have a little sniffer that measures the what? Partial pressure. Guess what the partial pressure of water is at 300 degrees K? 600 pascals. See, that's your partial pressure in equilibrium with the liquid. So it's kind of cool. There's like little hidden things in here that you may not even realize that are part of this thing that tell you these kinds of things. Okay, now the real thing though that's kind of cool is, why do things evaporate at all when I am square in the middle of the liquid plane? Actually, this is something I didn't get, don't even write this down, you know I'm just going off on tangents today. When you take 346, you're going to have Maxwell-Boltzmann distributions, which is something I'm going to introduce this Friday. To get you used to this, the proper way to calculate averages, because you learned it in calculus, but you forgot. What a Maxwell-Boltzmann distribution tells you is, and again, you're having this is 346, so you might as well see it now. This is a probability. Y is probability, and this is a certain speed. So when things, I think it's intuitive. that if I have a balloon, this is derived for gases, you're going to derive it next semester. If I have a balloon with gas in it, some are moving fast and some are moving slow. The reason that this can be a bit of a pain to deal with, which is what I'm going to go over next Friday, and how to deal with this mathematically, you see how it's bell-shaped but not quite? It's bell-shaped but slanted. It's slanted this way, so slanty bell. The problem with a slanty bell is that you're used to averages of, oh, take 10 numbers and divide by 10, and take 10 numbers, add them up, and divide by 10, that's your average. No, that's not true. It depends on the distribution. What you're thinking of, take 10 numbers and add them and divide by 10, is when your distribution, your probabilities are flat or are perfectly bell-shaped. This is neither. And so you can't calculate things based on probability like normal, like you're used to. Like I say, adding 10 numbers and divide by 10. It does not work. But regardless, I think it makes sense to you that some things are moving slowly, like they're cold, and some things are moving quickly, like they're hot. I mean, it just makes sense, you know, that on average things are moving with a certain amount of speed because they have a certain temperature, but some are just randomly behaving cold and some are behaving hot. All right, so what happens is, let's look at our box of water. Oh, it's Franja. Anyway, so I have it open, and here's the neat thing about everything I've been going over in terms of thermo. Thermo is a science of macroscopic length. Remember when we were doing some of that entropy stuff, KL and W, and I used the fact that if the number of gas molecules was really large, I used something called Stirling's approximation. It's okay if you don't recall, it's not going to be on the test. But some of the relationships I solved for were based on the fact that I have a large number of participants. But when I have a small number of participants, things can get out of hand. I can break thermodynamic principles if I'm looking small enough. And so if I'm looking at, say, a less than 1 nanometer by 1 nanometer scale, let's take water. I'll draw it like someone that got chopped in two like in Games of Thrones. Okay, so what can happen is that all of these water molecules just happen to fluctuate such that they all literally hit this molecule. And they energized it. And they energized it so much, it had enough energy, it had escape velocity. So much energy went into it that it ejected, and then the wind blew it away. Right? That's why the water eventually goes away. Now, did the pot get cold as a result? Yeah, of course it did. It had to. Your energy just went away. Right? And remember, molecules are energy. And it absorbed a bunch of energy like a sponge just randomly, and then it went somewhere else with it. So no, it actually got cold as a result. But why doesn't it freeze? Why doesn't it freeze? Someone said something about tobacco?
The environment.
Right, of course, the environment. I see. No, I'm actually kind of hard of hearing. Sometimes I hear weird things. Yeah, the environment. The environment heats back up, and you suck. So anyway, this is why that actually happens. Why you're liquid, why we can be in the liquid region, yet these nanometer scale fluctuations can also give us a gas, and here's its partial pressure. So neat stuff. And notice that if I heat things up, the partial pressure just rises and rises and rises until it gets to atmospheric. And the way to think about boiling is when your partial pressure is the same as atmospheric pressure, there's nothing holding you back. You can kind of think of a liquid that wants to boil but can't quite yet because the atmosphere is just pushing it down, literally. And at this temperature, you have enough oomph that you can push as hard right back, and then you can escape, and that's what I call boiling. Okay, so anyway, I hope that was kind of deep. But now the next thing I need to go over is, let me just redraw this thing again. Without numbers, I don't want it to be distracting. And here's the hint, here's the big hint, folks. We're going to be doing qualitative stuff, that's why I'm kind of being wonky today. We're going to start out doing a lot of qualitative stuff, but then we will get quantitative. In other words, let me tell you exactly what we're going to do. I'm going to be able to give you a triple point and say, hey, the triple point of water is here. And then I can ask you actually to mathematically draw these lines. I have to give you a starting point just because of the mathematics. But so when we get to that, which will probably be tomorrow, and it'll be on your homework, always, this is the time, I warned you about this. Despite the fact you've got pressure and volume and all that jazz, do not use anything but SI. If you don't, you will screw up. All right, so pascals, meters cubed for volume. Trust me on this, so just get that in your head. Always use SI units for any of the questions I ask on phase diagrams, because that whole kilopascal, liter thing does not happen in this case. We do not cancel each other out. So, the thing to go over now is, this is called Gibbs phase rule. I'll write that down in a second. If I am here, I'm going to have what I'm going to term as 2 degrees of freedom, and that means that I can go here and here, and still keep myself in a liquid phase. Okay, so degree of freedom, let me just tuck it underneath here. It's 2. 2 degrees of freedom, maybe just draw a little arrow or something, say that's degrees of freedom, not degrees of freedom like we had it before, where we're talking about rotating and doing pirouettes. And I know we're a little too. All right, so we're not talking about those degrees of freedom. It's that I can change temperature and pressure and maintain a liquid state. Now, of course, I can't go on forever, but let's not be idiots, all right? It's obvious what I mean there. Okay, now, if I'm on a interface, if I'm water boiling, I've only got 1. So if I've got a liquid and gas in equilibrium, it means I'm boiling in a box, let's put it that way. That way the water doesn't boil away. And so perfectly at 100 degrees, some of the water evaporates, some of the water condenses and comes back, and then it goes back and forth. I know this is horribly difficult to see, that I'm personally colorblind, so partially colorblind. Okay, here I've got 1 degree of freedom. Again, my liquid and gas in perfect equilibrium. If I make a change of temperature, then I must adjust the pressure just the right way to maintain that equilibrium. Otherwise, it'll boil off or it'll rain and condense completely. So, so again, 1 degree of freedom, meaning that when I change the temperature, because I just change it for the hell of it, I don't know, somebody leaned against the dial or something, then my pressure change was dictated to me. So I can decide to change this, but I can't decide how I change that. I do have to change it, but to maintain the equilibrium, I have to change it by nature's amount, and I don't have a choice. And here, at the triple point, I have 0 degrees of freedom, meaning that there's nothing. If I change temperature or pressure at all, I will lose my free-state equilibrium. And that's absolutely correct. No funny business there. And so, calculating degrees of freedom, here, let me write it out. This is a bit of a pain to do this. So this is called Gibbs phase rule. And what this is a function of all the variables that you can change, and figuring out how many can I change and how many can't I change. And because I'm talking about equilibrium, this is totally an equilibrium deal, I have to worry about pressure, temperature, chemical potentials, and mole fractions. You may notice that they're all intensive. They're all intensive variables. And remember, intensive variables define equilibrium. So when I say degrees of freedom, it's like, how much can I mess with these things? All right, temperature and pressure is easy in this case, but it does unfortunately get more complicated. And that's when, all right, so remember, this is a single component phase diagram. Multiple component phase diagrams are much harder to draw. I'm not going to start there, I'll do that later. But if this is water, and then I add ethanol, which I'm going to add ethanol, then it gets more complicated. And that means that the idea of number of variables I can control will change if I start dumping more things into the bucket. And let's see, what do I want to start with? Okay, so in terms of, all right, so again, we'll always talk about only adjusting intensive variables, because that's the only thing that really matters. So it looks like if I've got P and T, So P and D, yeah, that makes sense, because pressure and temperature are really defined. You know, like I say, if I got a cup of water with an ice cube in it, I better be at 0 degrees at 1 atmosphere pressure, otherwise they're not in equilibrium. If I am at those temperatures and pressures, then they're at equilibrium. So those are two things that I have pretty much no matter what. But like a triple point, I should be able to take some things off. But regardless, now this, again, you know, right now this looks trivial because this is a single component. So when you have multiple components, it gets harder. So let's add to that, okay, number of independent, sorry, now this is really long-winded, but just work with me here. All right, this is the number of independent constituents per phase. Number of independent constituents per phase. Okay, we'll call that C. Okay, this is probably kind of confusing right now. It'll be more clear next lecture, but for now, let's stick with ethanol water. C is 2. One is water, 2 is ethanol. If one can turn into the other via reaction, then this gets really confusing. That's where independent comes in. We're doing that on Wednesday. Let's not worry about it now. Right now, let's just say it's ethanol and water is 2. Now, that means that where's my new control? It's mole fractions, right? I can decide how much to add, and that's another thing I control, so that counts. And so, number of variables, let's see, I have 2 things, all right? And so that's 2 things I can control. And if I have a cup of water with an ice cube, and I pour some ethanol, not methanol, not be good. I pour some ethanol. Reality is that ice cube is going to absorb some of the ethanol too. Some of the ethanol will freeze, not a lot, all right, not a lot, but it will freeze. And that's something else I have control over. So it looks like, again, I've always got pressure and temperature, but given that I have all these mole fractions, that I've got this other thing, you know, decide. I have this other thing I can decide too. So again, let's talk about, let's drop the ice cube right now. Let's just talk about liquid ethanol and water. All right, so 1 phase, 2 components, that means I've got 2 plus 2. All right, so I can change temperature and pressure, and I can change the amount of water and ethanol. But that's a trick. It's not true. This is really, really subtle. This is the one part I like about this stuff. If I've got a mole fraction, I've decided ahead of time what I'm about my gin and tonic. I decided, because I'm hardcore, that it's going to be half water. What's the ethanol content? It's half water, the other half is... No, I'm going to add the gin, right? The other half is what? Gin. Half water, how much gin? Half. Half, okay. 1/4 water, how much gin? 4. That's real hard words. All right, now hold on a second. So in other words, I spit one number out and you give me the other, right? Right, there's only one, I have 2 things, but only one variable controls them. There's only a percentage for one of them, the other one is automatically defined. I have overcounted this, the degrees of freedom. I actually only had 1. And I can already tell that clearly I have 1, so it looks like I need to subtract 1, but really I got to start worrying about number of phases. So what's true of the water, let's bring back the ice cube, what's true of the water will be true of the ice cube as well. So when I've decided how much ethanol to pour in, and I've already got the water, it's already in there, so like I say, it's already been decided, the ice cube is also going to absorb a certain amount. And again, I don't really control that. I controlled it once when I poured the ethanol in, but I don't really control it beyond that. So it looks like I need to subtract P. Subtract P from that. So let's do our, let's drop the ice cube. Ethanol, water, 2, 1, minus 1 is 1. Right, one thing I can control, which is the mole fraction. Of 1, mole fraction, the other is decided. So that totally makes sense. Again, if it was a water ice cube, the number gets a little bit harder, so it would be 4 minus 2. 2 things. I don't really know what that means at this point. It's a little confusing to me, but anyway, that's how it works. So, and the way to know that is, I want your notes to make sense. Y minus P, the answer is because mole fractions, and let's also remind ourselves of notation. We've gone over this, it was a long time ago, of what, that would be like water, and this would be the ethanol, and that makes alpha, the phase, that would be the liquid phase. Let me throw in a third thing, just for the hell of it, and dot equals 1. And then I'm going to do the same thing for phase beta, for the ice cube. Plus chi c phase beta, plus dot, dot, dot. Okay, now, what it comes down to in terms of information theory, which is actual science, is that the way I know I've overcounted is because I have these equations that have equal signs. An equal sign is a constraint. An equal sign says you're going to have to do this. You have to obey me because I have an equal sign. They're not a greater or less than, an equal. So every equal sign is a constraint that I had to subtract off from my mistaken notion of how many degrees of freedom. And notice that I've got one equal sign for every phase. So there you go. That's exactly how it works. Okay, so now I've got plus Cp minus P. And you can imagine, unfortunately, it's going to get slightly worse. So, let's see here. I don't want to do this. I'll toss this up here and I'll come back to it in a second. It's almost done today anyway. I'll tell you one other neat little factoid about phase diagrams. Because, like I say, this stuff is kind of dry. Again, if I think about my ice cube, let me speed painting. My ice cube and my cup of water. There's other constraints as well. Well, I guess a cup should be a little higher than that, right? Yeah, there we go. And that is that, again, if I'm truly in equilibrium, then, let's see, chemical potentials have to be equal, right? The definition of chemical potentials at equilibrium is that they are equal. So let's say that for water in one phase, it has to be equal to the water in the other phase. So again, the chemical potential of water is equal to that of chemical potential of ice. And let me throw in a third phase, just because it kind of gets the point across. And then let's add in the ethanol, which would be B. And its liquid phase has to be in chemical potential equality with its ice cube phase, plus some other weird gas phase, I guess. Well, there would be a gas phase. There's vapor. Cops know it when they pull you over. You ever get pulled over and they are rubbing their pen in your face? It's not a pen, it's a breathalyzer, by the way, just so you know. I love giving away secrets of police. So, okay, now again, I know that this is true. And by the very act of creating equilibrium between A and B and there's 3 different phases, and I guess there's more stuff too if I add them, I see that I have more constraints and I have to subtract them off. All right, so basically the whole game is counting the number of equal signs and subtracting them off. Okay, so 3 phases, 2 equal signs. If I add another phase, add 4 phases, I have 3. If I have 5 phases, I have 4 equal signs. Okay. Again, 3 phases mean 2 equal signs. It means I have to subtract 2. But if I had 4 phases, I have 3. If I had 5, I have 4 equal signs. Come on. What do you think it is? Remember, it's P phases. How many equal signs? P minus 1. Right. All right, so P minus 1, I've got to subtract. And then I've now doubled them because I've doubled the amount of material. I added ethanol and water. Now I've got twice as many. If I had some turpentine, which I had because I'm a southerner, then I would have 3 times as many P minus 1 constraints, right? So P minus 1 times C. Times C, exactly right. Minus C times P minus 1. Okay. 2 plus CP minus P minus CP that right? Oh, no, minus, yeah, no, I got that right. It was, C minus B plus 2. Okay, so put a little box around that. That's Gibbs phase rule. So again, degrees of freedom, number of things you can change, whether it be temperature and pressure, they always get their special representations through here, or composition, or do I freeze it or not? How many things do I actually control is dictated by this thing here. Again, am I at a plane, a line, or a point is dictated by this. Let's example. Let's do examples. We got a little bit of time so I'm here, Nancy. Hold on 1 second. Let's do one component, one phase. Let's do 2 degrees of freedom. 2 ways I can go in temperature and pressure. Let's do this one. Let's do this guy here. Okay, I've got again 1 component, 2 phases. I mean, if you only change one thing, that'd be like temperature or pressure. Remember the others dictated. An example. I'm sorry if this makes your notes hard to follow, but okay, let's do the triple point. So I've got 1 component, 3 phases, 0. Yeah, that's right, 0. I won't screw that up. I'm still my tongue. That was really stupid. And so no degrees of freedom. Now, right, meaning you can't disturb anything and you'll lose your 3 phases. One of them will go away, if not 2 of them. So another important point is, now this is really good fodder, just ears up, maybe write this down. This is really good fodder for a true and false question. Why aren't there quadruple points, right? Why can't I have a 1 component phase diagram with a quadruple point? The answer would be that you have -1 degrees of freedom. That doesn't inherently make sense. That's like negative volumes, that's like negative pressures. They don't exist, and nor is there such a thing as a negative number of degrees of freedom. So 1 component phase diagrams never have anything beyond the triple point. Okay, well folks, I know it's maybe a little bit early, but there's not much else to say. So homework on Wednesday, and office hours if you have questions. See you on Wednesday. The last problem set, we're done. Then we have 2 tests.